Well, thank you, Mate. Looks like you reeled in a big one. I'm very excited to talk about machine learning on Databricks today. As mentioned, just as software has transformed many businesses and created new ones, AI will do the same. By definition, AI has been able to achieve tasks that previously wouldn't have been possible by manually writing software. However, we all know that most of the time spent in developing AI is focused on data, and that without good quality data, AI just doesn't work. So what is really happening is that data is the bigger beast that is eating AI. And while that may just sound like a catchphrase, there's actually a lot of truth to it. Let's take a look at why the focus is really on data. The main reason is that we've become really good at dealing with code and data separately, but we are terrible at combining them. In software engineering, the main goal is functional correctness, and in most cases, you can write good tests to ensure that. AI, on the other hand, tries to optimize a metric, which can be a moving target with changing data. Measuring quality in software is also easier, because it deterministically depends on code. However, in addition to code, the quality of a machine learning model depends on the data, model architecture, hyperparameters, and in some cases it can quite literally be random based on the random initialization of parameters. Finally, the outcome of software is deterministic, whereas in AI, the outcome of training a model can change significantly based on changes in the underlying data. All of these factors combined make it painfully clear that AI is hard because it depends neither on code nor on data alone, but on the combination of both. As a result, many different people need to get involved. I'm oversimplifying, of course, but software is mainly built by software engineers. To train a machine learning model and deploy it in production, on the other hand, you usually involve some combination of software engineers, data scientists, and data engineers. So getting all of these people involved and coordinating among them is a major challenge. Now, this is not uncommon, of course. Some of the most meaningful problems can only be solved by bringing many people together. However, it becomes almost impossible if those people cannot agree on the tools that they should use. In software development, usually a team standardizes on a stack, like which language, code versioning, or CI/CD system to use. And these tools have matured over time. In AI, I have seen many teams where different individuals prefer different machine learning frameworks, use different IDEs, and most certainly don't follow common CI/CD practices. In fact, this overview of the data and AI landscape by Matt Turk draws a perfect picture. Now, how you feel about this situation likely depends on who you are. If you are a VC or a researcher, you look at this landscape and you get excited. This is clearly a thriving ecosystem of innovation, with lots of opportunity for investments and PhD theses. However, if you're an enterprise architect who is responsible for making purchasing decisions, or a tech lead on a software engineering team, you probably think that this is a procurement and DevOps nightmare. You'll have to look at each one of these boxes and pick the right tool, and then spend lots of time and energy stitching them together. So the tooling is really hard because AI requires integrating many different components, and the space is moving at a breakneck pace. In summary, we are faced with three challenges. AI is hard because of the interdependency of code and data, many people needing to get involved, and a massive amount of components needing to be integrated. So what are the attributes of a solution? Well, first and foremost, since data is eating AI, the solution must be what we call data native. This is already where many machine learning platforms fail because they naively assume that the data problem is already taken care of. Secondly, data teams can really only be successful if they work together. So a solution better be collaborative and open to all members of a data team. And finally, the solution must integrate all components to satisfy the full machine learning lifecycle, and because the ecosystem moves at such a breakneck pace, it better follow open source standards. Many solutions out there fail to meet these requirements because they either disregard data engineering entirely, narrowly focus on only one persona within a data team, or they don't solve for the full machine learning lifecycle. Now, this would be a terrible keynote if I didn't have good news for you. If you know Databricks, you know that these attributes are at the core of what we do every day. And this has been a very long time coming. I'm extremely excited to announce the launch of a new product, Databricks Machine Learning. Databricks Machine Learning is a data-native and collaborative solution for the full machine learning lifecycle. It provides all of the capabilities needed for data teams to successfully train and deploy machine learning models and focus on their business needs as opposed to playing system integrators. So let's start with first things first. What do we mean by data native? As indicated on the bottom of this slide, Databricks Machine Learning is built on top of an open data lakehouse foundation. If you think about it, The first thing you should care about when picking a solution for machine learning is whether you can access any type of data at any scale from any source, which includes access to data across clouds. With Delta Lake, you can do just that. It doesn't matter whether you have images, video, tabular data, or whether those come in small files like CSVs or in terabytes of streaming data from IoT sensors. Delta Lake gives you consistent and high-performance access to all of your data. So what does this mean for machine learning specifically? When you train a model with the machine learning runtime, you benefit from optimized writes and reads to and from Delta, and because Delta provides ACID transaction guarantees, you can trust that your data are available at high quality and consistency. Delta also provides built-in data versioning through its time travel feature. Through an integration with MLflow, we automatically track exactly which version of your data you used when you train a specific model. That gives you full lineage from data to model and comes in handy when you think about reproducibility. So now that we've established what data native means, let's look at how the data science workspace makes Databricks machine learning collaborative. The data science workspace facilitates collaboration by supporting multi-language notebooks. You can use Scala, SQL, Python, or R, all within the same notebook. Now, the power of multi-language support really comes together once you collaborate with others. So the notebooks also provide cloud-native collaboration features like co-presence, co-editing, and commenting. And finally, and most importantly for machine learning, the workspace integrates tightly with MLflow. Here you can see the experiment sidebar that shows tracked parameters, metrics, and models, right within the context of your work. And at the core of Databricks machine learning, of course, are all of the components that facilitate machine learning from data to deployment and back. We start with data prep. As mentioned earlier, Databricks machine learning, being a data-native solution that is built on a lakehouse, supports any type of data at any scale. Now, there's more to this story than just being able to process any kind of data. Later in this talk, I have a surprise announcement for you that addresses machine learning-specific needs for data prep. Once your data is in shape, you can train models using any machine learning library you want. We provide a runtime that is optimized for machine learning and packages up the most popular ML libraries, like scikit-learn or TensorFlow, as well as popular tools for distributed training, hyperparameter tuning, or model interpretability. For model deployment, we support any and all deployment modes from batch to online scoring on the platform of your choice. Of course, as you know, Databricks is multi-cloud, so you can also train your model on one cloud and deploy it on another, or even on-prem or on edge devices. Getting to the foundation of machine learning, what is often referred to as MLOps, we found that true MLOps is really a combination between data ops, DevOps, and model ops. And of course, on Databricks, we combine all of these aspects with data versioning using Delta Lake, code versioning using our own new repos feature, and model lifecycle management with the MLflow model registry. But that's very abstract. Let's see what it looks like when you get MLOps right. And I like to explain this from right to left. Let's say you have a model deployed in production. You should be able to find out where it came from. The model registry shows you the entire history and approval workflow the model went through. From there, you may want to know the offline metrics and who trained the model. From the model registry, you can go back to the experiment that initially logged the model and find all of the metrics, parameters, and artifacts. And if that experiment was created on Databricks, we captured all of the environment information from your workspace as well. You can probably see where this is going. If you know the exact code that you used, the hardware configuration, library versions you installed, and the exact version of your data, we can give you a single button to reproduce the model. And we do just that. And this is really how you know that you've gotten MLOps right. So in summary, Databricks Machine Learning is a data-native and collaborative platform for the full machine learning lifecycle. But that's not all. As mentioned earlier, I have one or two surprise announcements for you. I'm extremely excited to announce a brand new addition to Databricks Machine Learning, a feature store. Our feature store is the first that was co-designed with a data and MLOps platform, and I'll walk you through what that means in a minute during the deep dive. And if that wasn't enough, we're also announcing today the release of our own native AutoML capability. Databricks AutoML is a unique glass-box approach to AutoML that empowers data teams without taking away control. Our customers love this approach to AutoML, and Casey will walk you through this new product later. But let's jump into the feature store first. All right, I'm extremely excited to talk to you about our feature store. Our feature store is the first feature store that has been co-designed with the Data and MLOps platform, which provides several differentiated features. Let's start by talking about what we mean by a feature. Let's use a recommendation system as an example. Your raw data may look something like this: a user table that has attributes of registered users, an items table that stores information about the items you're selling, and a purchases table that has a record of all of the items that users bought. Where you want to get to is a list of items ranked by the likelihood of a user purchasing them. So how do we get there? Well, with a machine learning model, of course. The inputs to a machine learning model are referred to as features, and the output is the prediction. What features can we think of? The most basic features are simple transformations. Let's say you have a product category and you want to encode that category as an integer when you feed it into the model. Context features are features that change with the context of where the prediction is made. That can be something as simple as the day of the week, or what device that user is using when they access your product. And in some cases, you may want to augment your data. One popular example is weather. You could access another data source to give you the weather in your user's location, which may help predict their purchasing behavior. And finally, a very common set of features that are used for recommendation systems are time window aggregates, like the number of purchases a user has made in different time periods. As you may imagine, some of these features, like a simple transformation, can be done by the model directly and don't require a feature store. But others, like time windowed aggregates, need to be pre-computed, stored in a feature store, and made available to the deployed model. So let's motivate the need for feature stores with a representative walkthrough of how data teams solve these challenges today. We start with raw data sources. The first time features are implemented is usually in an experimental setting. Data scientists often take the most expedient path, like copying code from Stack Overflow, to transform the data into the right features. Once data scientists found a model that works, it needs to be productionized. However, most often than not, the featureization code they wrote during experimentation doesn't quite work for a production setting. So the features are then re-implemented, sometimes by data engineering teams, to scale to the full data set. Now, if there's only one person working on one model, this may still be okay. But in big enterprises with large data teams, there is often another model that needs to be trained that consumes the same features. And because typically features are not easily discoverable and reusable, this whole process is repeated, even if the features are almost identical. This is the first big problem that feature stores address: no reuse of features. And once models are finally trained on the full production dataset, they're ready to be deployed. However, in order for the client application to make a valid request to the model, it needs to apply the same featureization that was applied at training time. Because that needs to happen within tens of milliseconds, the featureization is usually re-implemented once again, this time by the team that owns the client application. And these transformations need to be equivalent. Otherwise, you get something we call online-offline skew, where the model performs poorly because the online model behaves differently than the model that was trained offline, which is the second problem that feature stores address: online-offline skew and the complexity of avoiding it. So let's see how we can fix this. The first simplification that we will make is to only implement any given feature once. The feature store provides a feature registry that keeps track of all features that have been created and facilitates reuse across different models. We found that that alone saves multiple months of productivity in big data teams. Next, the feature store supports 2 access patterns that provide consistent versions of the features. The first is batch, for high throughput at training and batch inference. Model training can happen directly from the feature store. Because we co-designed the feature store with Delta Lake, it inherits all of its benefits. Most importantly, the data in the feature store is stored in an open format and can be accessed through native APIs. The same features are then made available at low latency for online serving. This guarantees that the features passed to the model from the client are the same as the features used in training time. Now, this already removes the need for re-implementing featureization in the client, because the features can be accessed directly from the feature store. And this is how most feature stores work. The client requests features from the feature store and then sends them to the model. But it still leaves complexity in the client. Like, for example, the client still needs to make sure that the versions of the features it requests are compatible with the versions of the model it calls. Because we co-designed the feature store with MLflow, when a model gets trained using the feature store, we store the information about which features it consumes with the model itself. As a result, in serving, the model can deal with the full complexity of looking up the right features from the feature store, and the client can be completely oblivious to the fact that the feature store exists in the first place. Now, this is important. As a result, features can be updated without any changes to the client, significantly simplifying the deployment process. So in summary, the Databricks Feature Store solves these two major problems through a feature registry that facilitates discoverability and reusability of features. Because we integrate with Delta and MLflow, we can provide upstream and downstream lineage. And a feature provider that gives consistent access to features at batch and online, and significantly simplifies the deployment process by packaging up feature lookup with the MLflow model itself. So let's see how that works. To add features to the feature store, you simply decorate the function that computes your features and call create feature table. Once features are registered, the feature store UI provides an overview of all feature tables. One thing I like to highlight here is automated data source tracking, which logs all data sources that were used in computing a specific feature table. With that information, you can search the UI by data source, which enables a key workflow for reusability. When a data scientist starts the work, they can search for all of the feature tables that have already been computed based on the same data. And on the feature details page, you can see the downstream lineage. The feature store records all of the consumers of features and provides a reference to them. This is critical when updating features or deciding whether you can deprecate a feature table or not. And of course, putting together upstream and downstream lineage, you can go from raw data to features that were computed on those data to the models that were trained using those features and back. From there, you can create training datasets directly from the feature store. This API takes care of joining of multiple feature tables based on the primary and foreign key relationships that are stored in the feature registry. And to access features online, all you have to do is to publish them to an online store. Note that there is no code example here of how to look up features from the client, because you don't have to. The model itself knows how to look up features, so the client stays unchanged. We are very excited to launch the Databricks Feature Store, and starting today, it is available in public preview to all Databricks customers. Of course, some of our customers had already early access and saw great benefits from using the Feature Store. ABN AMRO is a Dutch bank that uses Databricks to fight financial fraud. The Feature Store has been of great help to facilitate reuse of features and accelerate their model development. And with this, I'll hand it over to Casey, who will walk you through the second new component we're announcing today, AutoML.
Thanks, Clemens. Let's take a splash with AutoML. As Clemens mentioned earlier, we're very excited to announce Databricks AutoML is now in public preview. AutoML is a powerful tool that automates the machine learning development process from dataset to tuned model. This automation enables data scientists to quickly validate a machine learning project's feasibility, as well as get a baseline model to help guide the project's direction. In addition to solving these challenges, Databricks AutoML also addresses problems that we see in current AutoML solutions. In data teams, we always find a diverse set of people whose familiarity with AI is on a spectrum. On one end of the spectrum are experts, people with PhDs in AI. They know exactly what they are doing and they want full control. You can think of this as they want 3 pedals and a manual gearbox. On the next level are engineers, who may not have PhDs in AI, but they still want control. And they want the most tedious things taken care of for them. So they want something akin to automatic transmission. And at the other extreme are what we call citizen data scientists, and they have this expectation for full automation. But just like with autonomous cars, most solutions for citizen data scientists just don't quite work yet in AutoML. If you reach their limits and there's no way to take over control, all you can do is open the door and get out. And that's what we've seen with many of these citizen data science solutions in AutoML today. That's why we're excited to announce Databricks AutoML. Our approach is to augment rather than replace the data scientist by providing a low-code, automated solution where data scientists can take control and drive with their domain expertise at any time. Like most solutions, Databricks AutoML provides a UI interface as well as an API that takes a dataset and performs data pre-processing, feature engineering and selection, model training and tuning, and ultimately returns a recommended baseline model for deployment. Yet, unlike most solutions, we use CodeGen to enable data scientists to see exactly what is happening under the hood and provide them with the source code for each trial run in separate, modifiable Python notebooks. The transparency of our glass box approach makes it so, 1, you don't have to spend time reverse engineering an opaque model in order to make customizations using your domain expertise. And 2, if for regulatory reasons you need to show your work, you have the Python notebook that you can share to explain exactly how your model was trained. Furthermore, we integrate with all the Databricks ML features and ecosystem. For example, all AutoML experiments are linked with ML Flow, so they track all of the different parameters, metrics, artifacts, and models associated with every trial run so that you can easily compare your models and easily deploy through batch or online inference. And with that, we're looking forward to you all using Databricks AutoML to improve your team's productivity with these reproducible trial notebooks that give you that source code so that you can immediately modify these models and use your domain expertise to get a production-ready model. Now, let's go see all these different Databricks machine learning features in action in a demo.
Here we are inside of Databricks. To build a model to predict crypto mining for our security team, I need to make sure I'm using the new Databricks Machine Learning experience. Switching to this is going to change my left-hand side navigation to show me machine learning tools and features that are relevant to my day-to-day workflow. Because I'm unfamiliar with the security team's dataset for predicting Dogecoin mining, I'm going to use the new Databricks AutoML tool to jumpstart my development by having it generate a baseline model for me. Databricks AutoML is going to take a dataset and do all the pre-processing, feature engineering, model training, and tuning for me, and provide me with the source code for a baseline model for me to iterate on. So without further ado, let's start an AutoML experiment. On this page, the first thing I need to do is select a cluster. The next thing I need to do is select my problem type. Because I'm trying to identify whether or not someone is a crypto miner or is not a crypto miner, this is going to be a classification problem. I next need to find my security team's dataset, which here it is in usage logs. And from here, I can see a nice overview of this dataset schema, which is nice for me because I'm not really familiar with it, so it's a good refresher to see. A quick glance through, I can see that is mining is going to be my target, which means I can come down here and say that is mining is the feature that we're trying to predict. The last thing I want to do is check out advanced configuration. One of my top goals is to give the security team a quick yes/no answer on whether or not their dataset can be used to predict crypto miners. I'm going to use this timeout option in the advanced configuration to have a predictable runtime for my AutoML training so that I know I can get back to the security team within a day with an answer. Setting my timeout to 60 minutes means that AutoML will return the best model it can within that time frame. I'm going to leave it at this 1 hour and go ahead and click continue. With my basic configuration set up, I can now choose to augment my dataset with more features using the new Databricks Feature Store. Feature stores allow our team to share existing features between different ML projects. So rather than me having to spend time to create all these new features when I'm on a time crunch, I can instead utilize the features already created by my teammates. For example, this account features table is managed by my customer success team and has features relevant to a user's account. Because Databricks Machine Learning is a data-native platform built on top of a lakehouse architecture, it can intelligently suggest features I may want to join with to improve my training performance. As I said earlier, this is the customer success team's feature table, but it seems like it has relevant features to identifying a crypto miner, so I'm going to go ahead and accept this suggestion. I can explore and discover other feature tables in this dropdown, which my eye is caught on the IP feature table, which contains features related to the IP address, which again seems extremely relevant to identifying crypto miners. So we're going to go ahead and join on this. The only thing I have to do is I'll make sure that my primary keys are aligned. Before we start AutoML, there's one last thing to note. For this Dogecoin project, I'm going to be using both the offline and online feature stores. The Databricks Feature Store is going to help ensure consistency between these offline features that I'm using right now in training and these same features in the online store when I'm doing real-time inference so that the model behaves as predicted without any training or inference skew. And with that, let's now start AutoML training. Now that an hour has passed and AutoML has completed, I'm going to land on a page that looks like this. Because AutoML integrates with the Databricks machine learning experience, you can see that ML flow has been used to track all the models, parameters, and metrics associated with every trial run. This makes it extremely easy to compare each trial run and use my domain expertise to evaluate which model I want to use or iterate on for production. The other thing to note in this table is that it's sorted by the F1 score of the validation set, which is exactly what we said our evaluation metric was for AutoML. So the best model is at the top. Now, before I get too much into the weeds of comparing and evaluating these different trial runs, I was pretty unfamiliar with this security team's data set. So I kind of want to double check that this data set was fit for training. An easy way to do this is with the AutoML Data Exploration Notebook. AutoML provides a data exploration notebook to help me gut check my data and get quick insights. Much of this code is tedious to write, so data scientists like me may be tempted to skip this step to get to the more exciting part of building a model. Here you can see the Pandas profiler is being used to give me some basic summary stats. I can also see what warnings are associated with my data set. So here it just looks like some features have high cardinality, which for these specific features, it makes sense. And I can also see the distribution of my various variables. The main one I'm interested in is because I'm doing classification, I want to see if I have class imbalance. So I'm going to scroll to the bottom to my target, and sure enough, I can see that it looks like my classes are almost perfectly balanced. So I'm not worried about that. The last thing I want to check is my correlation matrix. If I come down here, I can see that in general, it looks good. It looks like event time might be correlated to my is mining target variable, but that kind of makes sense because we do think more and more mining activity is happening as people are really hoping to get to the moon. So now that I've used the data exploration notebook to gut check my data set, and I feel pretty confident that it was good enough to use in machine learning, I want to go ahead and register my baseline model to quickly build out an end-to-end proof of concept with real-time inference to see if I really can predict miners in real time. To do this, I'm going to go back to my experiment page, and I'm going to click this Register Best Model button. Here, I can create a new model to be tracked and managed inside the Databricks model registry. We're going to call this crypto detection. The Databricks Model Registry is a collaborative hub where teams can share ML models, integrate with governance workflows, and serve their models in real-time inference. On this model version page, I'm going to go ahead and promote this baseline model to the production stage. This is going to allow me to use real-time serving with it. We're going to go ahead and say baseline for proof of concept and transition it to production. Now that's in production, I can go to my main model page. I can go to the serving tab, and I can click in one button to enable serving. Serving is going to create a REST API endpoint so that I can call this endpoint from any app and get live predictions using this model. Now that my endpoint is live, we can test it out directly inside of Databricks. One of the cool things about AutoML is that it's helping me adopt best practices with ML flow. One of those things is to log an input example. Input examples are samples of your data set that you can then test your predictions on. So you can see here, I have some sample data that I can now feed in as a request, send it as a request, and get live predictions on whether or not someone's a crypto miner or not. Now, remember how we use the offline feature store to get features for training? Well, because we're in this data native environment, the model knows which offline features were used in training. And since that same model is being used in online scoring, it can automatically grab those same features from the online feature store for inference without me having to write any code. And to see further proof of this, you can come down to my logs, and I can see that sure enough, when I made this real-time call, the online feature store was used, and it grabbed features from my account features table and my IP features table. Great. So this is now the end-to-end of me building a proof of concept using a baseline model that I generated with AutoML. But I'm certain I can improve upon this best model using my domain expertise. And this is where the real power of Databricks AutoML comes in. If I navigate back to my experiment, one of the things that you'll notice here is this source column. In this source column, there are reproducible trial notebooks for every single trial run. And these notebooks contain the source code that trained that model. So you can see exactly how data is loaded, how one-hot encoding is done. You can see exactly how it was trained, which hyperparameters were used. And there's even a SHAP plot, so you can see which features were most important. Now, I have a hunch that crypto miners are probably newer accounts on the platform, especially since we've been seeing more and more mining related activity happening. So I'm going to derive a new feature called member recency in the model that calculates how much time has passed between a new account being created and a user finding an event on the platform. To do this, I'm just going to insert a new cell. I'm going to write my code that creates this new feature member recency. And then I'm just going to make sure when I go to my pipeline here that I've added this feature. And I should be good to go. All I need to do now is click run all, and it's going to run all this training code for me. And I will have the next version of my model that is now using my domain expertise. And I didn't have to reverse engineer anything. I could just make direct edits to the source code notebook to iterate on it and get a better model. So my notebook has just finished running, which again, this is using an AutoML generated notebook where I now created a new derived feature to improve my model performance. And a new trial run has been logged, which you can see by coming up to this top right. You can see that there's a little bubble letting me know that a new run has been added to my experiment. Let's go ahead and expand this experiment sidebar. And in here, I can change how my runs are sorted. So I'm going to sort it by the validation set F1 score, which is what AutoML had been ranking things on. And sure enough, I can see that this new run that we just logged is outperforming my AutoML baseline. And so my domain expertise did pull through here. So let's go ahead and register this new model that was logged. So now I can scroll to the bottom of this page. I can come down to my model artifacts and I can register this model. We're going to register it to the same as a new version to that previous model, crypto detection. And so I can go ahead and register this to the model registry. Again, the Databricks model registry usually would have an approval workflow between multiple people. So there'd be one person on your team who's requesting a transition for a model to go to production, and then you'd have an MLOps team that runs tests and validates that this model is ready to go into production and approves that transition request. However, because I'm working on this by myself and it's just a quick proof of concept, I'm just going to directly transition this model to production. And there we go. Now I'm going to go back to my model. You'll see that I have my two versions, my original AutoML baseline, and now my new version 2 that's using my domain expertise. And so now if I go back to my serving tab, we're now going to test my endpoint that now points to my new model version. Now that my endpoint is live, we can do exactly what we did before, where because AutoML used the ML flow best practices, it logged an input example for us. So we can see now this one has member recency. I can now send a request to get a live prediction from my serving, which we can now see our predictions on whether or not someone is doing crypto mining on our platform. And again, the online feature store was used to grab those features automatically for me. So Databricks Machine Learning has allowed me to get a quick baseline model that I could iterate on. It allowed me to discover features from the feature store that I could use to improve my model performance. It provided me with the source code for my trained models so that I could do customizations using my domain expertise. And then it automatically handled my online offline features and real-time servings to prevent any skew from happening.
The Databricks machine learning platform allowed me to build a machine learning model that could predict crypto miners in real time to help my security team identify the suspicious activity. We were able to do this in a data native way where all my data was in one location and I didn't have to pull it from various sources. We were able to do it in a collaborative way where I was able to work with my security team in Databricks to make sure that I had the right domain knowledge to build this model. And we did it from the whole ML lifecycle, from data set to deployment, all within a single location. And that's what the real power of Databricks ML is. Thank you all for joining us. And with that, I'm going to pass it off to Clemens.
Thank you, Casey. Very excited about these announcements. But wait, there's one more thing. You may be wondering how you get access to Databricks Machine Learning. We took all of these features, packaged them up nicely, and put a bow on it. As a unified platform, Databricks serves all members of a data team. So we're introducing a brand new persona-based navigation to Databricks so that each member of a data team has the right tools at their fingertips. Users can switch between data science and engineering and SQL analytics, and this is also where you will find the new machine learning experience. Of course, for those multi-talented among you, you can freely switch between options throughout your workflow. When you switch to machine learning, we surface the new machine learning capabilities and resources to you, including the new experiments page, the feature store UI, and the model registry. Some of our customers have gotten early access to all of these capabilities, and I'm happy to share their experiences so that you don't just have to take my word for it. Edmunds is a popular car shopping website that uses Databricks machine learning, among other things, for pricing vehicles on their website. Wildlife, one of the largest mobile gaming companies in the world, is using Databricks machine learning to personalize their user experience, which drives their top line. And H&M, the global fashion retailer, is using Databricks machine learning to parallelize model training for all of their countries, articles, and time periods. As you can see, companies across all industries can drive meaningful change with this solution, and so can you. So I'm happy to announce that all of the capabilities you saw in this keynote are available to all Databricks customers starting today. Of course, this was a lot of material, so to learn more, please check out our new website at databricks.com/ml.